A coil of wire of radius 3.0 centimeters is placed between the poles of an electromagnet. The field increases from 0 to 0.75 Tesla at a constant rate in a time interval of 225 seconds. What is the magnitude of the induced EMF in the coil if the field makes an angle of 30.0 degrees with the plane of the coil? Let's start with the sketch. We are given an electromagnet. So let's illustrate the magnetic field between the poles of this electromagnet. So this magnetic field will exit the North Pole and enter the South Pole of the electromagnet. We're told that this magnetic field increases from an initial value of 0 Tesla to a final value of 0.75 Tesla in 225 seconds. We're also told that we have a conducting loop, a coil of wire, placed within this magnetic field. This coil of wire has an orientation that is at an angle of 30 degrees with respect to the magnetic field. So let's indicate that angle as theta, and theta, the angle between the magnetic field and the plane of the loop, is given as 30.0 degrees. We're told that the loop has a radius of 3.0 centimeters. We need to find the magnitude of the induced EMF in this coil. From Faraday's law, we know that the induced EMF is equal to minus the time rate of change of the magnetic flux. Now remember, magnetic flux can change in one of two ways. It can change by the magnetic field changing, and it can change by the area changing. Since this coil of wire has a constant radius, its area isn't changing. So this means that the EMF induced in this coil of wire due to the rate of change of magnetic flux is given based off of the rate of change of the magnetic field. And our goal is to calculate the magnitude of this induced EMF. In order to calculate the magnitude of this induced EMF, we can represent the dot product between the area vector of the plane of the loop and the magnetic field as being equal to the product of the magnitude of the area vector, the magnitude of the time rate of change of the magnetic field, and the cosine of the angle between the area vector and the magnetic field. The area of the loop is equal to pi times the radius of the loop squared. And the magnetic field is changing at a constant rate. So the time rate of change of the magnetic field is just the change of magnetic field over the time interval in which it changes, times the cosine of the angle between the magnetic field and the area vector. So now we have all the parts. Let's go ahead and plug in the values that we have. The EMF is equal to pi times the radius squared. The radius is 3.0 times 10 to the minus 2 meters, quantity squared, times the final magnetic field, which is 0.75 Tesla, minus the initial magnitude of the magnetic field, which is 0 Tesla, over the time interval of 225 seconds, times the cosine of 30.0 degrees. When I plug this into my calculator, I get that the induced EMF is equal to 8.2 times 10 to the minus 6 volts, or 8.2 microvolts.